At the Convair division of General Dynamics, complex shapes of varying wall thickness are now being welded by an automated system employing direct computer control. This is a graphic cross-section of the cruise missile aft body, aft bulkhead weld joint area. It contains many curves of various radii, step-type jogs, severe corners of varying thickness, and a continuous constant radius with areas of tapering thickness. The three main axes of motion controlled by the computer are the ram drive, which translates the welding torch horizontally, a vertical motion to assist the voltage-controlled torch head, and the turntable of a welding positioner. Note the direct-mounted absolute shaft encoder, which provides true position data feedback to the computer. The welding power supply is a 400 ampere high-frequency pulsed arc, combination TIG-MIG unit. The operator sets the digital controls to the welding schedule. An electrically shielded cabinet houses the computer, telephone coupler, tape recorder, and interface modules. The 16,000-byte mini-computer controls the welding process directly, but must first be loaded with a program provided by the magnetic tape cassette. The program being loaded into the computer is called the data program. It provides the welding engineer or operator a convenient and highly efficient means of inspecting, modifying, or rewriting the entire data table. The instruction set at the top lists the tasks that can be performed on the 10 lines of the data table below. The column headings of the table include the position information, which are in polar coordinates, and the 5 main functions which can be continuously controlled by the computer. They are welding current, arc voltage, wire speed, turntable speed, and ram speed. An auxiliary function is available for switching other motors on and off and terminating the power supply sequence. A separate data table is, of course, needed for each weld joint configuration. New tapes and even a hard copy teletype printout can be made with this program. The control data table is developed directly on the CRT display screen by adding lines of data to the table as the weld schedule is developed. By changing lines, inserting lines, or deleting lines as required. When changing weld joints, the operator must insert a cassette containing the data table for the weld to be made. The tape is identified in several ways to assure the correct program is being loaded. Once loaded, it can be inspected on the display screen. The data program is then terminated, and the weld program is loaded and started. A single key push rotates the turntable to its programmed starting position. The torch is then manually jogged into a position in touch contact with the side wall of the cavity. The part, in this case the aft body section of a subsonic cruise missile, is leveled across its flat internal cavity plane and clamped to the turntable. This operation, called the set point, establishes an accurate relationship between the torch and the part and sets all ram position data in the computer. It can compensate for torch misalignment, off-center part mounting, and other such variables. After the set point is punched in, a third push of the same key commands the torch to travel to its programmed starting position for welding. The data table starting line normally line 1 unless doing a partial weld sequence, is entered, and the command data for the 5 basic controlled functions and the position readouts are displayed on the screen. The computer is online at this point, awaiting the RAM drive to be enabled. The power supply weld sequence is started with the push of a button, striking the arc of the fully automatic, self-completing weld cycle. The thickness of the square butt weld joint in the cavity area is just under a 1/4 inch. The material is alloy 2219 aluminum, welded in the aged condition, then re-aged after welding. Welding current and voltage, as well as the turntable speed, are programmed continually throughout these corners. An inherent part of the application program is to maintain the surface of the part level below the torch. This provides stability of the weld puddle, resulting in good bead contour, even in the most severe corner of short radius. All welding parameters are normally maintained constant in long, continuous areas, and the computer is reading the digital output of the drive encoder, in this case the turntable shaft position. The next table position flag triggers the computer to read the next data line from its memory. The next line at this joint contains a data word to command the torch rotation motor to operate. The torch arm assembly must be repositioned 180 degrees to permit re-entry into the cavity area from the opposite side. The weld is completed at the point of weld bead overlap. The rate of downslope of current and the RAM stop delay is programmed by the preset controls of the power supply. The assembly is then removed from the fixture, turned around, and remounted for welding the bulkhead on the opposite end. The weld configuration at this end, the aft end of the nacelle section, is considerably more complex, having 5 radii in the cavity, none of which center on the turntable axis. The only data needed to program these arcs were the polar coordinates of their centers. Using these coordinates, the computer calculates the necessary relationship between the two motions on a continuous, real-time basis and provides the proper commands to maintain it throughout the arc. The main command data and the position feedbacks of the RAM and turntable are continuously displayed throughout the welding cycle. The weld thickness increases in this area, calling for a programmed slowdown in table speed and increased welding current. Overall thickness of these weld joints varies from less than a 1/4 to about 3/8 of an inch. By making these welds in a single continuous pass, distortion in the assembly is held to a very low value. Holding major dimensions within 30 thousandths of an inch is not uncommon in welding these assemblies. The closure weld just made took an elapsed time of just under 6 minutes. The mid-body section, which will contain the missile's folding wings, again gets a bulkhead welded to each end. But it has 2 girth welds at each end, joining 2 D-shaped cylinders of the center section to the bulkheads. A weld certification specimen simulating one end of the mid-body is being welded here. The weld pass is started inside the wing slot, where it will overlap at completion. A torch arm of smaller profile is used in this restricted area. The torch is water-cooled and has an extra-large ceramic cup and gas lens which provide good gas coverage. It also has an oversized conductor cable for operating beyond its normal current rating. 300 amperes are delivered in some areas. A key to obtaining consistent weld penetration and bead contours is the use of a special pre-placed weld backup tape under the weld joint of production assemblies. The self-adhering tape is hand-laid in during fit-up and is simply pulled out after the welding. Prior to welding, the parts have had all dimensions held in the weld joint area to about 10% of nominal. After welding, the assembly is X-rayed. Defects, if any, found in the welds are very rarely attributed to the computer-controlled welding operation. This completed mid-body structure with its 4 computer-controlled welds shows that continuous single-pass welds can be made on production assemblies in unusually confined areas. This application of computer control provides product improvement and cost reductions which could be expanded to other manufacturing operations.